Welcome everyone, I'm J Wildberger, and we're engaging with some puzzles for young people, K to 6, which strengthen their arithmetical understanding by presenting them with some challenges. So we've already talked about some puzzles in the arithmetical direction. Today we're going to start thinking about some puzzles which have a measurement basis. And we're going to actually touch base with some interesting problems that suggest further directions of understanding and exploration. So maybe a few words about puzzles more generally. So we're talking about very young people here, right? So some of them may not be able to read, okay? So I'm really presenting the puzzles to the educators and to the teachers and parents of these children. So I'm hoping that you take these puzzles on board as potential directions to investigate with your children, okay? So there's also an element here of judgment required, because obviously the kinds of questions that you ask a kindergarten child that's going to be different from the ones you're asking a year 6 child. So I want you to adjust the level of the problems and be conscious of the fact that these puzzles have simpler versions. They also have more complicated versions. They're a little bit open-ended. So it's important for you to understand the situation first. But what I'm trying to do is trying to say, look, over here, this is a topic that's potentially of benefit for young people to learn about. So please introduce them to this topic through a puzzle in the direction that I'm suggesting. Okay, so some flexibility on your part is required. So our first puzzle is an arithmetical one, essentially. We're weighing things. We've got 3 things, actually, a boy, a cat, and a book. And we're asking, what are all the possible weights formed by combining some of these 3? A boy weighing 14 kilograms, let's say, a cat weighing 3 kilograms, and a book weighing 1 kilogram. So we can imagine a scale, and we're going to put a certain number of these objects on the scale and ask what are the totals that we can get. Okay, so the solution is that we have a number of additions to do. The possible totals are, and I've kind of put them here in some kind of reasonably logical order. First of all, the 0 solution when we decide to put none of the objects on the scale. Now, it's maybe a question of debate whether we should include that as a possible answer or not. And from the purely mathematical point of view, it turns out that it makes more sense to include that as part of the solution overall, okay? So we're going to put 0 there as the first possible weight that we can get. The book by itself gives us 1 kilogram. The cat by itself gives us 3 kilograms. The boy by himself is 14 kilograms. So those are possible weights that we can get rather obviously. And then we can weigh 2 of them together at a time. The book and the cat, making a total weight of 4. The book and the boy, a total weight of 15. And the cat and the boy, a total weight of 17. But then there's one more possible combination, which is to put all 3 of them together on the scale, if they all fit. And then we get 1 plus 3 plus 14, which is 18. So there are 8 possible solutions. Okay, and here they all are. And I've presented them in a sort of systematical way. That's something that we want to emphasize to the young children, that when we're doing this kind of problem, we shouldn't just be thinking, oh, that's a possibility, and that's a completely unrelated possibility. Now, we want to organize, right? We organize the solution, starting from the simplest ones and then working our way forward gradually, step by step, in an organized fashion. And if you have a more advanced student or an older student, then it's logical to proceed one more step and try the same question with 4 different weights. Okay? You have to be a little bit more systematic there. And there's a lot to learn by doing doing that question with 4 weights systematically and writing down all the solutions. So maybe I'll make this point also, that when we're doing these kinds of puzzles, it's not always cleverness that we're aiming for. We're also aiming for systematic thinking, organized, systematic, step-by-step thinking. All right, so our second puzzle, we're also weighing things. In this case, a boy and a girl. And we are told that the boy weighs 2 kilograms more than the girl. And we're also told that together they weigh 22 kilograms. And the question is, how much do they each weigh? So this is a nice question. So how do I want you to teach your young children how to think about such a question? Later on, when they become more sophisticated mathematically, they'll solve a question like this by introducing variables and doing equations. But that's actually quite a lot further down the road. We are nowhere near doing that, all right? So we do not want to present a solution that looks at all like that. What I want you to do is to approach this in a kind of a common sense, almost trial and error fashion. You know, what approximately would be a reasonable guess? Let's see what happens if we guess something and determine whether the result is lower or higher than what we're aiming for, and then adjust the guess correspondingly. Okay, so there's a kind of a strategy underlying here, which is actually very important, to make an estimation, see what happens with that guess, and then adjust the guess the next time around depending on where your initial answer lies with respect to where you want to be. So let's illustrate that here. So together they're going to weigh 22 kilograms. So maybe the girl weighs 8 kilograms. In that case, the boy would weigh 2 more, which would be 10. And their total would be 10 plus 8, which is 18 kilograms. Okay, that's under what we're looking for, right? So we have to have a sense of order. We have to realize that 18 is less than 22. So we want to up the weights of the boy and the girl. Okay, so let's try something bigger. How about if the girl weighs 12 kilograms? And I'm going to introduce this little shorthand, if G equals 12. Okay, so G stands for the weight of the girl, but we don't have to be too formal about that. We could just sort of write that down informally so the student starts to see how we're using a little symbol to represent what it is that we're looking for. So if G is 12, the girl weighs 12 kilograms, then the boy will weigh 2 more, which is 14, and then we have to do a bit of arithmetic. We have to somehow add these two things, and hopefully we can do that one way or the other and get a total of 26. Comparing that with 22, that's too high. So we started too low, now we're too high. Okay, so we have to adjust. So let's go down a little bit. If G equals 11, then B equals 13, and the sum is 24. Still a little bit too high. Let's go down a little bit further. If G equals 10, then B equals 12, then G plus B equals 22. That's great. That's exactly what we want. So the answer is G equals 10, the girl weighs 10, and the boy weighs 12 kilograms. Now, I've chosen certain numbers here, okay? So the numbers that I've chosen I think would be sort of suitable for sort of a mid-level student in the age bracket we're thinking about. But if you're starting with a very young child, these numbers are perhaps too big, right? So you would want to give them a version of this puzzle which has smaller numbers. Say you have a kindergarten child, okay? You want to ask them a question like this. Well, you could simplify it. You could say that a boy weighs 1 kilogram more than a girl. That's a lot easier. And so in your mind, you could think 1 kilogram, maybe one of them weighs 5 and the other one weighs 6. And then the total would be 11. So the question would be, boy weighs 1 kilogram more than a girl. Together they weigh 11 kilograms. How much do they each weigh? Okay, well, that'd be very low total. Maybe cats would be more suitable. Okay, but anyway, you get the idea that what we want to do is we want to adjust the numbers in these puzzles to suit the level and the aptitude and the experience of the children that we're talking about. All right, so our third puzzle, we might call it the heavier ball puzzle, is a very classical puzzle that's familiar and has a lot of different variants also. So again, there's additional kinds of questions in the same direction that we could ask. And in the course that I'm designing, there will be lots of other examples in this kind of direction. So the story here is that we've got 9 identical looking balls, and one of them is slightly heavier than the others. The others are all the same weight, but one of them is heavier than the others. But we don't know which because they all look exactly the same. Now, we're trying to find that heavier ball, and what we have is a pan balance. Okay, so we're able to put things in 2 pans and see which one is heavier or whether they're equal. And we're trying to determine the heavier ball using exactly 2 weighings, 2 uses of the pan balance. Okay, so this problem is already a little bit, extensive. It involves a fair number of things. There's 9 balls. So it's not a bad idea probably to start this kind of investigation with a simpler example. So the simpler example would be what happens if you have 3 balls and one of them is heavier. Okay, so let's just think about that one first because that's actually involved in this one. Okay, so if you have 3 balls, let's call them 1, 2, 3, okay? And one of them is heavier, but you don't know which one. What you're gonna do is you can take 2 of those balls, say ball number 1 and ball number 2, and you're gonna put them in the pan balance. And if they are equal, well then those are the 2 equal balls. It must be that the third ball, number 3, is the heavier ball. On the other hand, if they're not equal, say 1 is heavier than 2, well then the 1 is heavier than 2, and so 1 must be the heaviest ball of all 3, because we know that the 2 lighter balls have the same weight. Okay? So that's how we determine the heaviest ball if we just have 3 of them. Okay, so that's a kind of a preliminary that we can do first before we tackle the main puzzle. But if you have a clever child, maybe you don't need to have that discussion beforehand. You can let them work that out as part of the puzzle. Okay, so you have to kind of assess what preliminary training you should have with your student. Okay, so here is our solution now. So if the balls are numbered, say 1, 2, up to 9, then let's start by weighing with the pan balance the balls 1, 2, and 3 in one pan and the ones 4, 5, and 6 in the other pan. Okay, we put them in there and see what happens. If they are equal, then it follows that none of these 6 balls is the heavier one that we're looking for. None of them, okay? So we can put them aside and concentrate on the other 3 balls. Then we're in that situation that we just were in, that we've solved. So what you do then is you would weigh 2 of them, say 7 and 8, and quickly determine then which of those 3 was the heaviest. On the other hand, if the initial groups of 3 were unequal, okay, then you're going to take 2 from the heavier pan. So for example, suppose that the 1, 2, 3 pan was heavier, 1, 2, 3. That means that the heavier ball is one of the triple 1, 2, and 3. So again, we apply what we've already talked about. We would take 2 of those balls, say 1 and 2, and weigh them. And from that, we would deduce which of the 3 balls is the heaviest. On the other hand, if when we weigh these 2 sets, the 4, 5, and 6 ball set are the heaviest, then again, we would apply the same reasoning to those 3 balls, take 2 of them, say ball 4 and 5, and weigh them and deduce which of 4, 5, and 6 was the heaviest. So we have to kind of go through the possibilities here. It's not exactly a linear thing. It's more like a tree kind of structure. If this happens, we go in this direction. If this happens, we go in this direction. Okay? So this is a great puzzle because it's teaching children the importance of a kind of a logical structure. If this, we go in this direction. If this, we go in this direction. There's different possibilities, and we have to deal with those possibilities in slightly different fashions. Although ultimately, it comes down to the same underlying idea that once you know that the heaviest ball is one of three, then you can determine which it is with just one way. Now, there's all kinds of interesting variants to this puzzle also. For example, you might know that one of the balls is different, but not know whether it's lighter or heavier. Or you could have, two of the balls being heavier. Or you could have, instead of having 9 balls, you could have, 20 balls. And there's all kinds of variants that you could discuss in the same direction. So there's a lot of exploring to do behind this particular puzzle. That's why it's such a classic one. Okay, our next puzzle is also very instructive and actually practically quite important. We can easily convince some young people of the usefulness of being able to solve this particular puzzle. And in fact, historically, exactly this kind of puzzle would have been wrestled with by ancient peoples. Okay? We're talking about creating standardized weights in order to be able to weigh things using a pan balance. That's the context. Okay, so we want to weigh objects using a pan balance, like this, and 4 standardized weights. So we're going to create 4 standardized weights. 1, 2, 3, 4. We're going to have these 4 physical weights that we're going to be able to use. And we're going to agree that the object will be in one pan, like over here. Maybe that's a tomato or something. And the standardized weights will be in the other. So object in one pan, standardized weights in the other. And we want to weigh the object. That means we want to create a balanced situation. For example, here, there's a standardized weight of 1, a standardized weight of 5 in the left pan. So if there's balance, we deduce that the weight of the object is 1 plus 5, which is 6. Okay, so we're going to assume now that the object that we're weighing weighs a whole number of ounces. We're going to shift to the imperial or US system of weights, talk about ounces. And I remind you that 16 ounces make a pound. And a pound is a little bit less than half a kilogram if you're coming from the metrical system. All right? So 16 ounces make a pound. So we're going to assume that we have some object and it weighs a whole number of ounces. So what do we mean by that? Well, it means that it's exactly 1 ounce or 2 ounces or 3 ounces or 4 ounces, something like that. It's not some fraction between 2 of those whole numbers. Okay? So usually when we weigh things, we expect there's a dial and we get some reading, which is generally approximate and not exactly a whole number. Okay? But we're assuming here that our objects are exactly whole numbers of ounces. And we're going to restrict ourselves to the number of ounces that the thing weighs, being 1 to 15. Somewhere in that range. The object could weigh 1 ounce, it could weigh 15 ounces, or it could weigh any whole number of ounces in between that. Now, after all that preliminary, what is the actual puzzle? The puzzle is to figure out what is the best choice for the 4 standardized weights that we're going to create. We want to create 4 standardized weights, and we get to choose the weights of those 4 standardized weights. And we want to choose them well so that with just those 4 weights, we are able to weigh any object in this range. So this is obviously an interesting and useful question. And pleasantly, it also connects very naturally with some important mathematics relating to the binary system. Actually, to a situation that we've already discussed in the arithmetical context in our previous video. But we don't have to say that to our children who are wrestling with this. Okay, so this is an important and interesting puzzle, which is a kind of a to-do. Okay, we are trying to figure out how to make this work. So what we're going to do is we're going to go through the possible weights of objects that we're going to potentially weigh from 1 to 15. And we're going to adjust our idea of the standardized weights so that at each stage we'll be able to weigh all the objects up to that particular stage that we're at. So let's start with the simplest possible object. If we have something weighing 1 ounce and we want to weigh that using a pan balance in the way that we've described, there's really only one way of doing that. So we need a weight of 1 ounce, and we'll illustrate that with this little black box that represents our standardized weight of weight 1 ounce. So we have one of those. And now what about an object weighing 2 ounces? We want to weigh that also. Now at this stage we have two choices. We already have a 1 ounce standardized weight. What we could do is create a second one. So now we have 2 of them. And with those 2, we could weigh our 2 ounce object. We could determine that this is 2 ounces by putting 2 standardized 1 ounce weights in the pan. But that would not be the most efficient way of proceeding because there's some duplication there, and it's more efficient for us to introduce a 2 ounce weight instead. We already have a 1 ounce weight. Let's now introduce a 2 ounce weight, and we'll use that to weigh something that weighs 2 ounces. Well, then we're also able to weigh something weighing 3 ounces because 3 is 1 plus 2. But after that, we're going to require a new standardized weight of 4 because there's no way for us to weigh something weighing 4 ounces if we just have a 1 and a 2 ounce standardized weights. Okay, so we have to introduce a 4 ounce standardized weight. And then with the 1, the 2, and the 4 that we have up to this point, we are then able to weigh something weighing 5 ounces because that'll be 1 plus 4. 6 ounces because that'll be 2 plus 4. And 7 ounces because that will be 1 plus 2 plus 4. So we'll be good up to and including 7. But 8 we will need a new standardized weight for. So finally we need also a standardized weight of weight 8 ounces. And then we need to check that with these 4 standardized weights, 1, 2, 4, and 8, we're then able to weigh all the remaining weights from 9 through 15. So let me do that verbally, although we can also write it down on a piece of paper. How do we weigh something weighing 9 ounces? Well, we use the 1 and the 8. They combine to give us 9. And 10 ounces, we use 2 and 8. They combine to give us 10. 11 ounces, that would be 1 plus 2 plus 8. 12 ounces would be 4 plus 8. 13 ounces would be 1 plus 4 plus 8. 14 ounces would be 2 plus 4 plus 8. And 15 ounces would be, all 4 of them, 1 plus 2 plus 4 plus 8. Arithmetically, hopefully, the student will say, wait a minute, we've done this same kind of thing back in the previous week when we were talking about that puzzle involving row rectangles and expressing row rectangles in terms of 1s, 2s, 4s, and 8s. It's really arithmetically the same. But now we're thinking about it in a different way. Now we're thinking in terms of actually having physical standardized weights. And that's a kind of application of this arithmetic, which is going to be useful because if we have to weigh things with a pan balance, then exactly this technology is going to be useful for us. And hopefully, for the more advanced students, more experienced ones, after we've gone this far, they'll be wanting to say, and what happens if we go further? What would be the next weight that we would need to introduce? Well, obviously, it's going to be the weight of 16. And then how far will that allow us to go? And what will be the next one, etc. So the importance of the powers of 2 and sort of binary representations of things, although we don't have to use that terminology, it's already becoming intuitively clear to the students, because they're making these computations, summing up using powers of 2. So it's a very important kind of direction of familiarity with arithmetic. So this is a good puzzle. Now our final puzzle is a variant on the previous one, and quite an interesting one that I think will be more novel to many of you viewers also. So there'll be something for you to learn here as well. We're going to be looking at the same kind of situation. We're still trying to weigh objects using a pan balance. We're still in the imperial US system with ounces. And we're still restricting ourselves to whole number of ounces, the objects that we're weighing. But what we're going to be doing now is allowing ourselves a little bit more flexibility about how we use the standardized weights. In fact, maybe this is even something that could occur to a young student. If you're playing around here, they might have this idea. Why do we need, actually, since we have these 2 pans in the pan balance, why do we need to insist that the object is in one pan and all the standardized weights that we're going to be using are in the other one? Couldn't we maybe combine them? Couldn't we have a situation like this, where there's the object in red, labeled with X, and over here we have standardized weights of, say, 2 and 5, and over here there's a standardized weight of 3. Now, suppose those 2 total weights balance. What could we deduce? Well, 2 plus 5, the left-hand side here, would have to equal X, whatever that is, plus 3. All right, so what must X be for this? Well, 2 plus 5 is 7. So X plus 3 is 7. So what do we have to add to 3 to get 7? Well, we have to add 4. So we could deduce from this that X has to be 4. So in this situation, we're able to deduce that this object has weight 4, even though we don't have 4 standardized weight, and even though we're not able, with these 3 standardized weights, to get a total of 4 on one side. But by combining them on both sides, we are able to weigh something of weight 4. So that's the basic idea, okay? We're looking for an improved technology, an improved way of using standardized weights and a pan balance to weigh stuff. Hopefully, that will allow us more efficiency. We'll be able to save costs. In fact, that's exactly what happens here. Okay, so the common sense, practical application of this should be quite obvious even to young children. Okay, so here is the puzzle officially. We want to weigh objects with a pan balance, and this time 3 standardized weights to make it just a little bit simpler. Okay, we have 3 standardized weights. But we're going to agree that now the standardized weights can be in either pan, just like here. Okay. And in order to weigh objects still of a whole number of ounces, and I'm not going to go from 1 up to a certain amount. I'm just going to say let's try to ensure that we can weigh all the objects with a whole number of ounces, starting from 1, including 2, including 3, including 4, up to however far we can go. But we don't want to miss any one of those. Okay, so we want to have a way of doing each one of those weights using only our 3 standardized weights that we have to choose. So what is the best choice for our 3 standardized weights? And how far in this sequence can we go successfully? We can weigh whole number of weights up to how much? Now this is a little bit of a tricky problem, and it's maybe a little bit unfamiliar, so I suggest that educators and parents, you might want to pause the video now and spend a little bit of time yourselves thinking about how you're going to solve this problem. Okay, so let me sort of kind of go through a way of thinking about this. We want to concentrate on the step-by-step procedure that we're going to be aiming for here, right? So we want to be systematic. We want to emphasize the importance of writing things down systematically. Okay, the student may not be really good at writing sentences and so on, but we can still write little equations involving arithmetic, and we want to do that sequentially, one line at a time, in a way that the student can then get a sense of the movement as we progress up through the possible weights. So let's start with a weight of 1. I'll put it over here on the right-hand side. Okay, so that's a weight of 1 that we want to balance. And in order to balance that, well, we need a little standardized weight of weight 1. So we are going to require, just as we did in the previous question, a standardized weight of weight 1. Let's put that there, all right? We're going to need that. Now, we want to weigh something that weighs 2 ounces. How could we do that? Well, one way, of course, would be to introduce a 2-ounce standardized weight, as we did in the previous case. But actually, we can do something a little bit more clever by the fact that we can use the 1 standardized weight that we already have. And we can put that on this side, 1. And then to balance things, what we really want is another standardized weight, to make it a little bit bigger, weight 3. Okay. So if we introduce a standardized weight of weight 3, then exploiting the fact that we're able to use our standardized weights on either pan, then we can weigh an object weighing 2 ounces by creating this configuration. 2-ounce object plus a 1-ounce standardized weight on one side and a 3-ounce standardized weight on the other. We have balance. We can deduce that that thing has to be 2 ounces because 1 plus 2 equals 3. Okay, so that's going to be our next standardized weight. It's a 3. Okay, so let's do some more weighing. How do we weigh something that weighs 3 ounces? Well, we're just going to use the standardized weight of 3. That's easy. And how about something that weighs 4? How are we going to weigh that? Well, we're going to use the 1 that we already have plus the 3 that we now have, and that will balance with 4. So 4 is good. How about 5? 5. Can we weigh 5 just with the 1 and the 3? No, we can't. We now need a new standardized weight. And now we have to scratch our heads and pause and think carefully for a minute. Which standardized weight are we now going to introduce? Of course, we could introduce 5. But that's not the most efficient thing to do. That's not the cleverest thing to do. You could also use 6 or 7, but neither of those is the cleverest thing to do. The clever thing to do is to realize that we could weigh 5 by putting the totals that we already have, the 1 and the 3, plus 3 over in the same pan as the 5. And then that would form a total of 9. And so if we're able to have a standardized weight of 9 ounces, we can balance this situation and determine that that's 5. So let me make a thicker one like this. So there is one of weight 9. So there's our third weight. 9. Okay, what about 6? How would we weigh that? Well, that's one more than the previous, so what we should do is kind of get rid of that 1 that's sitting there and just use the 3. And then over here, we still have a 9. So yes, we're able to weigh something weighing 6 ounces. What about 7? Well, 7, we could also have a 3 on this side. That would give us a total of 10. And can we cook up a 10 with the other 2? Well, yes, we can, because we can write that as 1 plus our 9. So we can also weigh something weighing 7 ounces. And now we can actually proceed, and I'm going to let you figure out how to do the remaining ones. And it turns out that we can keep going up to well, kind of obvious what the largest one is going to be, right? The largest one is going to be when we use all of these 3 on the one side. So I'll put the 13 over here, and that's equal to that's a 1 and a 3 and our 9. Okay, 1 plus 3 plus 9 is 13. And of course, there are the intermediate ones, which I'm leaving to you. So that's part of the story. You have to write them down, but I'm going to leave you to do that. And so that's as far as we can go with these 3 standardized weights. So this is more efficient than with the 1, 2, and 4, right? With the 1, 2, and 4 weights, we can only go up to 7. Now we're going up to 13 because we're more flexible about using the pan balance. We're using the pan balance sort of in a more sensible way, really. So this is great because, first of all, it's a little bit clever. We're getting the students to think about, the importance of balancing, that we can put stuff on either side of the balance. That's so important when it comes to doing arithmetic and algebra later on, because an equation is very much like a balancing situation, very much like that, okay? So this idea of moving from a 1 from this side to another side, how does that affect the rest? That's really good practice for later on learning to be confident about manipulating equations. And also it's intrinsically interesting and naturally suggests, what should be the next weight that we should introduce if we want to go further. And hopefully you'll be able to figure that out. And hopefully even a good primary school student will be able, after some thinking, to make a good guess as to what that next standardized weight in this sequence ought to be. So we see here that there's an interesting alternative to the important binary system involving powers of 2. That's such a big part of our world. Here in the standardized weight story, there's also powers of something else floating around here, isn't there? All right, so great. So in our next video, we're going to carry on with some more puzzles, more challenges having to do with measurement, but we're going to introduce some measurements of volume and capacity, some challenges in that direction. Hope you'll join me for that. I'm J Wildberger. Thanks for listening.